The pumping lemma for CFGs proves that no PDA exists that accepts the language of strings where some number of A's are followed by the same number of B's and then the same number of C's. So we created a new type of computer, a Turing machine. But will Turing machines accept this language? Let's see if we can build one. Now, a human might decide if a string like this is in the language by counting the number of A's, then comparing them to the number of B's and C's. But this requires storing the number of A's, which can only be done using the states of the Turing machine. And we need one state for each number. A1 would be a state where there's one A, A2 a state where there's two A's, A3 a state where there's three A's, and so on, which we can't have, because we have to have a finite number of states. But remember, do one thing at a time, and if we need to do a lot of things, we should use recursion over and over. So instead, we might imagine looking at the first A. In order for the string to be in the language, there must be a matching B and C as well, which we can find, and we can delete all three. Now lather, rinse, repeat. Now our Turing machine for the language of palindromes gave us two useful strategies, going from an initial state Q0 to a ready-to-work state Q1, and then deleting the symbols read as long as we don't need them afterwards. So from our initial state Q0, we'll move right and enter state Q1. This gives us the move if we're in Q0 and read blank, change to state Q1, print blank, and move right. For the other moves, a useful strategy, work on acceptance first. In other words, start by making sure the Turing machine accepts a string it's supposed to. So if our Turing machine has been given a string it should accept, then the first symbol it reads should be A. So if we're in state Q1 and read A, we should delete it, print blank, then move right. Do we need to change states? Note that if we're in state Q1, reading an A will cause us to delete it and move right. So if we stay in state Q1, we delete all the A's, which we don't want to do just yet. So we need to change states to something new, call it QA, giving us the move. Q1A gives us QA blank right. Now in state QA, we'll want to move right as long as we read an A. Since we only want to delete one A at a time, we'll need to reprint the A's after we read them, giving us delta QA A, stays in state QA, prints A, and moves right. But if we read B, we'll need to delete it and move right. As with the first A, we have to change states to avoid deleting the other B's, giving us the move. And will move us right until we encounter a C. Once we read the first C, we'll need to return to the beginning. So we'll want to switch to a move left state L and define the move delta QB C moves us into state QL, prints blank, and moves left. Now as long as we encounter a B, we'll keep moving left. So we'll define the move. But notice there's a blank which we printed between the B's and the A's. So we need to also move left if we encounter a blank, and then move across the A's by And there's a problem. Since our Turing machine moves left if it reads a blank, and there's a blank at the beginning, the Turing machine will continue to move left until it tries to move past the start of the tape. So it will crash. So how can we get around that? We'll take a look at that next.